In this video, we will discuss how to record measurements using the correct number of significant figures to reflect precision. There are two types of numbers used in science: exact numbers and measured values. Exact numbers are defined quantities. For example, 1 dozen is defined as exactly 12 items. A dozen donuts is 12 donuts, and a dozen eggs is 12 eggs. Another example is 1 week is exactly 7 days. Exact numbers can also be counted values, such as the number of tires on a car or the number of people in a room. Measured values, on the other hand, always have some degree of uncertainty. Some measurements are more uncertain than others, but all measured values must include units. In the lab, you will use both digital and analog equipment. The image shown here is an analytical balance, which is a digital instrument used to measure mass. Some analytical balances are more precise than others, but you should always record all the digits displayed on the balance. This particular balance measures mass to 4 decimal places. The mass of the metal bar shown would be recorded as 54.5828 grams. Other lab instruments are analog, meaning they have printed lines or divisions rather than a digital display. For analog instruments, it's our job to interpret the spacing of those lines to determine the instrument's precision. The image shown here is a graduated cylinder. It has labeled markings at 10, 15, and 20 milliliters, with smaller lines in between representing 11, 12, 13, and 14 milliliters. A graduated cylinder can be used to measure volume using the displacement method. In this method, the cylinder is filled with water and the initial volume is recorded. An object is then submerged, and the change in water level is used to determine the object's volume. When recording measured values, we care about both accuracy and precision. Accuracy refers to how close a measurement is to the true value or accepted value. Precision refers to how close repeated measurements are to one another. A set of measurements can be precise without being accurate, and vice versa. Every piece of lab equipment has specific precision. For analog instruments, we determine this precision by examining the spacing of the lines. Some digits are known with certainty because they correspond to marked lines. In addition to these known digits, we must always include one estimated digit. The estimated digit represents our best guess as to where the measurement falls between the two lines. Finally, every measurement must include a unit. Let's start by looking at the beaker shown. The labeled lines are at 10, 20, and 30 milliliters, meaning there is a 10 milliliter difference between each line. This tells us that the tens place is known. Any measurement made with this beaker will have a known digit in the tens place and an estimated digit in the ones place, giving the template KE. The liquid level is between 20 and 30 milliliters and past the halfway point, so it is greater than 25 milliliters. A reasonable estimate would be 28 milliliters, though values between 27 and 29 milliliters would be acceptable. Next, consider the graduated cylinder shown. The labeled lines are at 27, 28, and 29 milliliters, which are 1 milliliter apart. This tells us that the ones place is known. If the volume is greater than 10 milliliters, then the tens place is also known. This means that the estimated digit will be in the tenths place, giving us the template KK decimal E. The liquid level is slightly above 28, milliliters, so a reasonable estimate is 28.2 milliliters. Values between 28.1 and 28.3 milliliters would also be acceptable. Now let's consider the burette shown. The numbered lines are at 28 and 29 milliliters, and the lines between them represent tenths of a milliliter. This means the tens, ones, and tenths place are known, and the estimated digit is in the hundredths place. The template for this measurement is KK period KE. The liquid level is just above 28.3 line, so the reasonable measurement is 28.31 milliliters. If you believed the liquid level is exactly on the 28.3 line, you would record the measurement as 28.30 milliliters. That 0 is important because it is your estimated digit. Comparing these instruments, the beaker is the least precise because the estimated digit is in the ones place. The burette is the most precise because the estimated digit is in the hundredths place. The smaller estimated digit means measurements will be closer together and more precise. In the lab, beakers are not used for precise measurements. Beakers are like cups in the kitchen, while graduated cylinders and burettes are more like measuring cups. Now look at the images below and record the measurements for each. Starting with image A, the numbered lines are 26 and 27, which are 1 unit apart. This tells us that the ones place is known. The smaller lines in between them represent tenths, so the tenths is also known. The measurement template is KK.KE. Start at the smaller number and count upwards. Always read from the bottom of the meniscus, which is the lowest point of the curve. The liquid level is at 26.8 and appears more than halfway towards the 26.9. So a reasonable estimate is 26.87 milliliters. For image B, the labeled lines are at 30 and 40 milliliters, which are 10 units apart. This means the tens digit is known. The smaller divisions represent ones, so the ones place is also known. The estimated digit will be in the tenths place, giving us the template KK.E. The bottom of the meniscus is exactly on the 30 milliliter line, but we must still include an estimated digit. The measurement should be recorded as 30.0 milliliters. Next, look at image C. The line spacing is the same as image B, so the same template applies. KK.E. Labeling the lines between 30 and 40, we see that the bottom of the meniscus is above 37 and below 38 milliliters. Reading from the bottom of the meniscus, a reasonable estimate is about 37.3 milliliters. Finally, consider image D, which shows a ruler measuring in centimeters. The ones place is known, and the division between each centimeter represents tenths of a centimeter. This means that the ones and tenths place are also known, and the estimated digit is in the hundredths place. The measurement template is KK.KE. The metal object is very close to the 3.8 centimeter mark. If you believe it is exactly on the line, you would record the measurement as 3.80 centimeters. If you believe it is slightly before the line, you would record as 3.79 centimeters.